Welcome back to Week Freeze Post Videos. Today we're going to look at the Perceptron learning algorithm and look at its convergence. It's a basic proof, but it illustrates several important concepts, and we're going to break it down into 3 different steps. Let's get started now. So if you remember Perceptron Convergence, basically we saw that we could find some misclassified examples, right? I'm going to call those xi, so some data point in the data set. The IF point which is misclassified. And we're going to multiply it against its label yi, and this will be the weight update that we're going to apply to the current weight vector to get out a new weight vector. And we saw sometimes when we correct a misclassification, so here in iteration 2 we chose this point, and we updated the weight vector into something like this, which got all of the additional blue points over here incorrected. Right, it misclassified them. So now we want to show that when we do the perceptron updates, we're going to converge eventually to a finite number of iterations. It won't be, going back and forth and correcting points and getting other ones wrong, and then finally it's going to get a good classifier. Right, so we want to know, whether this question is true. Is it possible that these weight updates actually never terminate when the data is linearly separable? And to do that, we're going to start with some terminology to help us get through our proof. So to distinguish with respect to the values before and after, we're going to use this new notation of k and k plus 1. So for example, before we had written something like this: theta prime equals theta plus yi and xi, which is the misclassified example. Instead of writing something like this, we're going to write a notation that's a little bit more comprehensive, because now the problem is that we will need to distinguish between different iterations. Okay, so we're going to write something like this instead. Theta of the k plus 1 iteration equals theta of the k iteration plus y of that particular iteration plus times the misclassified example at the kth iteration. Something along those lines, okay? And we're also going to use this notation here. This notation here is probably familiar to some of you. So we already know when we have single vertical lines, we have an absolute value. But here we're going to use double vertical lines to denote a norm. And we're just going to use a superscript 2 to denote its square. Okay, so whatever expression we're going to put inside here is going to be the square of the norm of that particular data point. All right? So I said we're going to do this proof in several steps. So we're going to be doing a proof by contradiction, which hopefully many of you are familiar with. We're going to show that the updating process has to stop after a finite number of iterations. If it doesn't converge, then basically what will happen is we'll never stop doing the update rule. We're going to be applying this continuously ad infinitum, and we're going to show that that's not possible to do. So the line of argument for the proof is like this. We're going to first find an upper bound, which is linear, for how much time the norm is going to be able to change from its initial value. Let's say its initial value is set to all zeros. So maybe we're going to initialize a theta to a column of all zeros, so that all of the coefficients that we're multiplying against the observations are 0. Okay, so what we're going to do is start with from that point and then iterate, right? So every iteration, remember, we're only considering the iterations that find a misclassified example. We're going to be updating the weights. So we're going to show that there's an upper bound for that. So secondly, we're going to find a quadratic lower bound for how much the weight vector has to change from its initial value after k iterations. So we have an upper bound and a lower bound, and where theta will actually change will be somewhere in this region here. And we're just going to show, because of the way that proof works, that there's got to be some point in which the two curves are going to meet, and that's going to be the maximum number of iterations that PLA learning is going to take to get a convergence. So it could stop earlier. It might be the case that perceptron learning goes something like this, and then, oh, it found a separating hyperplane and it stops at this point. But we're just saying that there's a maximum number of iterations that it can go before these two curves hit each other, and that's the maximum that it's going to take. So just to recap, we saw that our original update is like this, that I just wrote on the last slide. And this means that for positive misclassifications, meaning that we had incorrectly thought of it as a positive case, right? Then we need to multiply that correct classification, which is actually a negative, times the actual value. So we're going to get out this case where we're subtracting just the vector of the misclassified example as the weight update. And for negative misclassifications, it's the exact opposite, right? So we're going to flip the negative sign to a plus. So we'll have the original weight vector, and then we're just going to add in a plus there. But to make it easier math-wise, we want to combine both of the classes into a single condition. So we're going to multiply the negative case, which would contribute to the positive misclassifications over here, by -1. So we're going to be able to add everything together. Right? So we can say that the correct parameter setting, let's say there is one, and there must be one if we have Perceptron Convergence, which means that we actually find a separating hyperplane between two classes. We'll call that theta star, such that theta star times all of the examples in the data set, all of the JF examples from 1 to m are going to satisfy this condition that the weight vector times class are going to be above 0. And then our update equation is just going to be very simple. It's always just going to be an addition of the misclassified examples point, so that we're going to update the weight vector according to that. So we're basically nudging the weight vector in such a way to always get the point classified correctly. So if you can think about it like this, we have some positive examples, we have some negative examples, and let's say one of the negative examples is misclassified right now. When we do this weight update, we're just trying to push the weight vector towards the correct place. So this is the norm, and then we're just trying to move it somewhere like this. Okay, so that's the idea behind what we're doing. And now you're going to watch two other segments to show the upper and lower bound and put it all together.